तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello and welcome everybody again. We have been discussing in the last class the concept of area subdivision method for VSD algorithms or visible surface detection algorithm. Okay. And this is one of the sequence of half a dozen algorithms which we are going to discuss in this lecture series. To just recast, we have discussed backface culling, then the depth buffer or Z buffer based method, and then of course, the scan line based method, and then the depth sorting or painter's algorithm. And we have discussed at the end of the last class the area subdivision method. So, just going back to those illustrations which distinguish these four possible relationships between a rectangular subimage and a polygon, based on which we either render or split a polygon, split a rectangular area of interest into four equal parts, is the following. So, if you look back into the slide, so these are the four cases of polygon position with respect to the rectangular area of interest. You can have a surrounding polygon, you can have an intersecting polygon, you can have a contained polygon or a disjoint polygon with respect to a rectangular area of interest, which is marked by the gray color inside this. And as mentioned in the last class, you must remember that you do not have to worry about polygons which are disjoint, do not even consider them under any circumstances. The contained and intersecting are considered as same, identical. It means, what do you mean by identical? We said that one of the points was that if you find there is only one polygon which is intersecting or it is contained within the area of interest, what you have to do is paint the rectangular area of interest with the background color first, and then paint the polygon with the corresponding color of the polygon. So, that one, that is over. And then of course, we had the other case of a surrounding polygon. If there is one surrounding polygon, of course, use the color of the polygon to render that particular area of interest, mind you, not the entire polygon must be rendered, only that rectangular area of interest, which could be the entire image or a part of the image under consideration to paint, we must paint with that particular polygonal color if that polygon is surrounding the entire area of interest. Now, these are the cases which we have seen in this slide earlier, if there is only one. Now, the case comes when there are more than one polygon. When there are more than one polygon, that is the case which we have to consider. Of course, in those cases, do not consider any disjoint polygons, and still if there are more than one, that is two or more polygons within the rectangular area of interest and various relationships exist, of course, again only surrounding, contained and intersection relationships are to be considered. Disjoint cases are not considered, keep in mind. So, now you have more than one polygon. Under that, we have a special case where there is one surrounding polygon in front, which we can, if we can find out by the help of the z coordinate intersection test with respect to these four vertices of the rectangular parallelepiped viewport, the parallel to z axis. If you have visualized rectangular cube parallelepiped and you are viewing through a viewport and you are visualizing that there are so many polygons inside and there is one in front of you, the closest to you, which is surrounding all other or obscuring all other polygons, then you should use that particular polygon to paint that rectangular area of interest. Otherwise, so if none of these cases happen, that means you are not having a single polygon case, number one, you are having multiple polygons, and out of this you are not able to find out one surrounding polygon which is in front of you. So, if none of these cases happen, what do? You split the rectangular area of interest into four parts. That is what you do, and keep on subdividing. This is why it is called a divide and conquer strategy, working in the image space, and you keep on subdividing starting from the root node. Remember the quadratic representation which we talked about for an image. Take the entire image, split into four parts, four quadrants if necessary. We did this in the Bresenham's line algorithm case, ellipse and circle as well. and we talked about a quartile representation, extension of that was octaves in the case of solid modeling in 3D. So, I repeat again, quartile representation 4 parts, each of those sub images or 4 quadrants could be again subdivided if necessary. You keep on doing that till you may reach, in a certain case, if you keep on subdividing into the maximum resolution, the maximum height or the level of the depth of the tree which you get is just 1 pixel resolution. You might reach a 1 pixel resolution at the maximum level of the tree, that if you keep on splitting and so on, you will reach 1 pixel where you cannot subdivide any further, and that case of course, what you have to do is you have to render that pixel with what polygon is in front of you corresponding to that particular pixel. So, that is what we were discussing, and we pick up a few case studies as examples of area subdivision method. Okay, couple of examples as we did for other cases also, here we pick up a few more case studies. Let us look at this simple example. Stage 1 to be analyzed, where within the entire image there are 2 polygons, in this case they are 2 triangles. So, if you passed all those 4 tests, there is, first of all, there is no single polygon within the area of interest. What is the area of interest AOI here? The entire image. The entire image is your area of interest, and you find that there are more than 1 polygon, and there is no single surrounding polygon. There is no single surrounding polygon which is in front of you. So, there is no other option but to split this area of interest, in this case the starting image, into 4 equal parts or 4 quadrants. So, do that and let us see what happens. When you split, this is what results in. Okay. Of course, you split and do some processing, and that is what the result which you get. If you split this entire image into 4 parts, let us say we have 4 quadrants, northeast, northwest, southwest, southeast. We will take this as quadrant number 1, 2, 3 and 4. 4 children of a root node. Okay. The entire tree is split into 4 parts, 4 children is what you have, and those are the quadrants 1, 2, 3 and 4. Okay. So, quadrant 1, 2, 3 and 4. 4 parts as you can see here. So, and you start analyzing them one by one. Let us start with quadrant number 2. It is a very simple case of an intersecting case. Intersecting content is same. What do you do when you find an intersecting polygon, a single one? You paint with a background color, which is in this case white as I have chosen here, but it could be black, does not matter, and the rest of the part of that quadrant you paint with that intersecting overlapping polygon. And this concept holds good for quadrant 2, 3 and 4. All the 3 quadrants will have a case of intersecting polygon and single one, and we know what to do in all of these cases. It is the same case, you paint first with the background color and then paint with the polygon which is overlapping with that particular AOI or area of interest. We are talking of quadrants 2, 3 and 4, okay, not quadrant 1. Okay. The quadrant 1 will be here. So, 2, 3 and 4 is what you are looking, and for all these 2, 3 and 4 quadrants you have an intersecting case, and that is what you have done. So, the quadrants 2, 3 and 4 have been processed, quadrant 2, 3 and 4. Quadrant number 1 is a special case. What happens in quadrant 1? If you carefully watch, it contains 2 polygons again, like the original case of 2 polygons, and there is no surrounding polygon in front. So, quadrant number 1 is the only quadrant out of these 4 after the first split. After the first split you got 4 quadrants, is not it? And the 3 out of those 4 was a contained intersecting case, intersecting polygon. Only quadrant number 1 had a scenario where you had 2 polygons and there is no surrounding polygon in front. So, you have to split quadrant number 1 again into 4 further subdivisions, which results in a scenario like this. I repeat again, quadrant 2, 3 and 4 have been already processed and you do not need to subdivide further. Quadrant number 1 here in stage number 2 is split into 4 equal parts, as in stage number 3 into 4 other subquadrants. And again, as you can see in this split, now you have 4 area of interest. This subquadrant 1 is a case of a disjoint, it is only a background color. So, you do not have to use any polygon, simply put the background color in that, and that processes this particular subregion. Okay, this particular subregion only background color. What about this subquadrant? Okay, that is an intersecting case. So, you put the background color first and then put the overlapping that part of the intersecting polygon. quadrant number 2, 1, 2 and similarly 4 same case, 4 same case. Quadrant 3 is a problem. Why? Because you have 2 polygons and again none of them is in front. So, that is the one which you need to split further. So, when you split that particular part, this is what you will result in. Okay. That final part here which is not processed at stage number 3 will be processed at stage number 4, which will give you 4 sub quadrants again at level 3 decomposition at the 4th stage, first, second and third level of decomposition. Here you have 2 sub quadrants at that stage which is produced, which will be disjoint cases filled by the background color. This will be filled with a probably a surrounding or an intersecting polygon as the case may be, and of course, this is definitely a case with the brown color rectangular patch which will be an intersecting polygon. So, at the end of this stage you will have no further subdivision necessary, because the entire image has been covered with smaller subdivision quadrants or regions of interest, each of them either subdivided or at the end of the maximum level of resolution you have smaller sub images or region of interest which only have the background color or single polygon case, surrounding, contain or intersecting. Disjoint of course is background color. So, if you look back again, as I rewind this stage is here, this was the initial case split into 4 parts, 3 quadrants are handled, 1 quadrant left, first quadrant split again into 4 parts, you will have again 3 quadrants processed very comfortably, only 1 quadrant having to split that part into again 4 parts, and that is the final result which you will get. That is the final result which you will get after subdivision. So, this is an example only with 2 polygons, where you have to go for subdivisions up to 3 levels to actually. I leave it as an exercise for you to alter these positions of these 2 triangles or even the shapes of these 2 triangles and position it in a graph paper at different position and start splitting and exercising. Take this as a home exercise where you interchange these positions of these 2 triangles or take 2 different triangles with 2 different shapes and start splitting if necessary. You can take a small pencil, scale and paper and work this problem out yourself with 2 polygons with 2 different shapes at 2 different positions. That is what you do in the area subdivision method. But an important lesson to be learnt here, if you just carefully watch the figure again, which is if you compare the original scenario at stage number 1 before any subdivision and the final result which you have got, if you compare stage 1 and 4, you see that the maximum number of subdivision is occurring at situations where there are adjacent polygons close by, and that too you are operating more at near the edges or the vertices of the polygons. So, where there are more the overlap, okay, more number of vertices around a certain area of interest, you need more and more subdivisions, and the complexity of this algorithm in image space subdivision is a very difficult guess. Of course, the maximum number of subdivision is if you have an image of resolution n pixels by n pixels, n could be 1024, 640 by 480 or 1024 or 12, whatever the case may be. Of course, the maximum level of decomposition which you can go is log n steps, that is of course true. That is the worst case which you can. Case of course, an average case can be computed, but average very difficult to compute because it all depends upon the number of triangles which you have or polygons which you have, the position of the relative positions of those polygons, relative positions of those edges and vertices. The more closer you have the edges and vertices of 2 different polygons closer together or overlapping more, the more subdivision you will have, and that is where you need to spend more time. As you can see here, when you compare stage 1 initial stage and stage 4 final stage, the subdivision is somewhere around here, where there is more of bit of overlap. In other places where there is a background or only one single polygon, you do not need to subdivide. If you add a third polygon, you can visualize that you need to have more subdivisions necessary in cases where the edges of that third polygon will be overlap into nearby edges of the other 2 polygons. And you can almost visualize such a stage that you will have go on subdividing more and more. Of course, you can't go beyond the pixel resolution, all right, but if you have to go to that pixel resolution, the complexity of subdivision and testing goes and more higher and higher, which you cannot avoid, but you have to do, and that is the main degree of complexity of the area subdivision method, main bottleneck of computational time necessary is subdivision and testing, and more number of polygons overlapping, their edges and vertices coming closer together will cause more subdivision. I will just give a final example based on which you can visualize that if you look in this particular case, just two triangles again completely overlapping as much as possible. As you can see here, this is the final result of subdivision. So, where do you find the subdivisions getting more? It is at those edges which are overlapping those areas and the vertices, okay, which is overlapping certain areas. So, as long as the two triangles or polygons would have been separated out, the number of subdivisions would have been, but it would have been less. But the more closer you get, more overlap you make, now more vertices and edges overlapping and then coming closer, the more the subdivision necessary. If you look at this particular figure, you can visualize that the first stage is of course 4 quadrants, and the most simplest case out of these 4 sub quadrants which you will get, the first level of sub quadrants, sub images is the first, second, third one. Third one is the only case where you have one intersecting polygon. I think it is clear that sub quadrant is the only one. Third, where you have no other polygons, but just one intersecting polygon, easily paint with the background color and then the polygon, that part which is overlapping. So, that part which is done. Third one, first, second and fourth polygons have to be subdivided. If you examine the second one, that is also little better in the sense that you would subdivide further into 4 parts. This part is background, this part is background as pointed to by my arrow here, and then you have this part which is intersecting, single intersection. Here also you have a single intersection. It is only in this sub quadrant, one out of the second one, where you have to divide into 4 parts, because there is a small part of this polygon here and another polygon there, which is getting into the picture, okay, which is getting into the picture. So, that is the problem which you have. If you carefully, there is a triangle here and there is a deeper polygon triangle which is on the back side, and a frontal polygon here which I am drawing on the screen here, and then what you have is these two polygons will split into 4 parts, background here, intersecting here, intersecting here. This may need to split into 4 parts, but you do not have to split further beyond this, because you have again 2 background disjoint case, and these 2 carefully, if you watch, small sections of intersecting cases. So, that handles quadrant number 2 and 3. Quadrant number 1 and 4, massive amount of splitting necessary with maximum level of decomposition. So, in some cases it might go to even 1 pixel. Along the edge and near the vertices, the splits are more and more as necessary. If you go back to the figure here, in some case the splits will be handling the case where you have intersecting here as well as there in these 3 cases. But look at this sub quadrant and this part here, you have more and more splits, and more so along the edges and near to the vertices. Okay, you can visualize this yourself, because if you could have worked out, it would have taken a long time. I leave this as an exercise for you to try it out yourself, starting from scratch, taking 2 overlapping triangles and start splitting, and as you can see, the splittings will mostly occur along the edges. Now, if this is a scenario with only 2 polygons with part overlap, of course, the previous example which you have taken was also 2 triangles, but since there was no overlap, the subdivisions were 2 stages, but it was less. But here in this case, if you see 2 polygons, quite a bit extent of overlap, huge number of splitting of the area subdivision necessary, and more so along the edges and the vertex which is overlapping another polygon with 2 only. If you have 3 or even more, as the number of polygons increase more and more, you can visualize the complexity. It's possible that almost the entire image or entire sub images, the quadrants after the first level of decomposition have to be split further and further, and more so we have to go to the maximum resolution of 1 pixel for most of the splitting cases. Most of them have to be split to the maximum level of resolution of 1 pixel. In certain cases, of course, you will be lucky to get a background only or 1 intersecting case. So, this was the last example. We talked about area subdivision method. You can almost visualize the amount of complexity which you will have, and it is working in the image space using divide and conquer based method. It is not a very popular method, but conceptually the algorithm is very nice. We move on to the next section called the BSP tree based method, or binary space partition tree. BSP trees or binary space partition tree is based on the concept of subdivision, but in the object space. Let us look at this particular diagram. Binary space partition trees, we have 3 polygonal surfaces, and I have purposefully taken a curved surface. This is a 3-dimensional figure you need to visualize. that there are two triangle polygonal patches and there is a curved surface as well. Do not worry about it right now, which is labeled D. The C here, and this polygon we will see is marked as AB, we will see why. Now, what is done is the following. You imagine a plane P1 with a surface normal pointing towards the brighter side. Remember this brighter and darker side of a polygon. Okay, so, that is the brighter side which is pointing towards the viewer, and this P1 plane is splitting your three dimensional space into a front partition and a back partition. This concept should not be new to you. We have seen this in many cases. A line splits a two dimensional space into two equal half planes. We have done this in clipping, we have even done this in Bresenham's line algorithm, okay, where the implicit functional form becomes positive 0 at the line and negative below the line. Okay, you can have a vertical horizontal line in clipping, which we talk of an inside half plane and outside half plane also. So, if that is in 3D, I am sorry, that if that is in 2D, then in 3D also if you talk of clipping or not, you can visualize a plane, and that plane will be splitting your three dimensional space or volume into two semi infinite sub volumes. So, we will talk of this as a front partition and a back partition. This space in your room, let us say you imagine a plane, and the plane splits your space into a frontal and a back. What is front and back depends upon the viewing direction, all right, or we have put a normal vector to that surface which is splitting the plane, and that normal vector is computed based on the concept of brighter and darker side with respect to the viewer. Remember that concept of anti-clockwise ordering of the vertices to get the correct interpretation of the surface normal, to interpret the brighter side and not the darker side. So, with respect to the brighter side, you have the front partition of the space in 3D and the back side on the back partition on the darker side. So, that is what is done in this figure, where we split the three dimensional space. This is a three dimensional figure. The plane P1 splits the three dimensional space into a front and a back partition. Once that is done, what will happen is, this is what will result, that under P1 with P1 as the root node, I can visualize a binary tree, okay, with the links and the edges between the children of P1 with the root node as P1 labeled as front and back, depending upon we talk of a front partition and a back partition, and under that we have the say the surfaces on one side of P1 and the other side of P1. Okay. So, what are on the front side of P1? A and C are on the front side, which is the left children of P1, and B and D are on the other side. So, it is possible that this triangular polygon has to be split into two partitions A and B. A will be on the front partition and B will be on the back partition. This of course, using a plane to split a polygon in two parts, we have done already in one of the other VSD algorithms, okay, in the last lecture. If you remember, what did we use it? We used it in the case of Painter's algorithm, depth sorting, where we wanted to avoid infinite loop and we used a polygon to split another polygonal plane into two parts. So, that is what is also done here, where the P1 is used to split this bigger triangle AB into two smaller partitions, and we will say that is A and B. Okay. And then again what I do, I use another imaginary plane P2 with this vector pointing in the front brighter direction, and with respect to P2 also I will have a front partition and a back partition. Okay. So, I will say here I have a P2F, okay. I have a P2F and a P2B, which basically means I am worried about the back side. So, I use the same plane on the frontal side. So, P2F is on the part of the plane P2 which is on the front side of with respect to P1, and this P2B indicates part of the plane P2 which is on the back side with respect to P1, that is all. So, P2F and P2B are nothing but this plane P2, but front and back with respect to plane P1, because I will use P2F, a plane which is on the frontal side of P1 or the front partition of P1, and I use it to sub-partition the space further. So, what I am basically doing, let us say I imagine a plane here where this entire classroom is split into two parts, okay. I have a plane in between. So, I have, let us say this is the front plane on your right hand side, and this is the black plane which you have on your left hand side. Okay. So, this is your right hand side which you have the front plane, and this is the back plane which you have to your left hand side. What I do now is, after taking this as P1, I use a P to another plane. Let us say, assume for the timing that is orthogonal, although it could be any arbitrary plane which is non-parallel to P1, preferably. It should be intersecting P1. So, what will happen? This frontal side of with respect to P1 will be further split into two parts. Okay, and similarly, the back side of this with respect to this P1, the back side which you have will also be split into two further parts. So, you will have 4 parts now, something like your quadtree representation, all right, but in 2D, but in this case in this object space. But if you project this space partition into a 2-dimensional scenario projection plane, you can visualize this to be something like a quadtree type of splitting. Okay. So, one plane splits into 2 parts, select another plane, these 2 are again into 2 and so on. So, that I can use this a binary tree type of representation. Unlike a quadtree, I use purposefully this quadtree, because at each root node and other siblings of all nodes will either have polygons which are inside the 3D scene, or partitions or split parts of the polygons, or it could have some imaginary surfaces sitting which are dividing this the entire space or a subspace in 3D, the front or the back at any level of decomposition in 3D, mind you, into 2 more further parts. Okay. So, each node is a plane or a polygon. The polygon plane could be a polygon out of those, we will see that. That is what is usually done. Okay. And that plane is used to split that zone or 3-dimensional space into 2 further parts, and since it is always 2 parts which you are splitting by any plane, a binary tree is a very straightforward and a simple way of representing this type of splitting. Okay. Automatically you can use simply a binary space partition, that is why is the name given, and binary tree is a good data structure which can represent this splitting of this 3D space into 2 parts. So, let us complete this figure. As you see here, the imaginary plane P1 is splitting the space into 2 parts, front and back, and in the frontal part you use a P2F, under which you have the frontal side, this A part of this bigger triangle. So, that is what you put A, and the back side with respect to P2, which is the right child of P2F, will be this polygon C. What is on the back side with respect to P1? This part, where you have B and D. So, what you do? You use the plane P2B, which is this plane, the back side of P2 plane, split this plane into 2 further parts. On the left child, you have the frontal part, which is B, which is put here, and the curved surface D is put on the right child, which is because it is on the back side with respect to P2. So, I hope with this simple example you are able to understand what is the concept of binary space partition, that is representing 3D trees and 3D space with respect to binary trees, where each child will either, if they, at the leaf nodes you will have of course the polygons or the split parts of the polygons. All higher ups you will have imaginary planes, or it could be these polygons which are also could be used to split the plane. So, that is what you use. So, salient features of BSP trees based VSD algorithms are the following. Identify surfaces that are inside or the front. These words are used interchangeably, inside front and outside back. So, you can use inside outside to represent the concept of or front and back as complementary partitions. Okay. So, either you can use inside, same meaning as front, or vice versa, outside or back we will use interchangeably. We will keep the word front and back, but you can also use inside outside. You remember the inside outside for a line within a 2D space or a plane with respect to 3D, inside half plane, outside half plane. So, it is a similar concept here, front and back or inside outside are we use interchangeably. So, coming back to this sentence again, identify surfaces that are in inside front as and outside back with respect to the partitioning plane at each space of subdivision relative to the viewing direction. Okay. I repeat again, identify the surfaces that are in front and the back of the partitioning plane at each space of the subdivision relative to the viewing direction. And start with any plane and find one set of objects behind and rest in the front. Now, we talked of this previous example as an imaginary plane P1 and another imaginary plane P2, but nobody stops you from taking one of the n polygons in the 3D scene as your imaginary plane or the plane which you are using as your root node and to split the entire 3D space into 2 parts, and after you have classified or categorized or grouped the remaining planes n minus 1 planes into 2 halves, you use from each of these categories one more plane each to split into further subdivisions to construct this binary space tree or binary tree as it is called. Okay. So, the imaginary planes may not exist anymore because that will add to the computation. You have to actually come up with an equation for that planar surface. Why don't you use the polygons which themselves could be planes? So, that is what is used. So, start with any of these planar polygons as a plane to split and find one set of objects which are behind, that is one category, and the rest is another category which is in the front. In the tree, the objects are represented as terminal nodes with front objects as left branches and back objects as right branches. So, I already told you, because the binary tree will have a left subtree or siblings, in fact not siblings, it is a left subtree and a right subtree, and the left subtree will contain all the polygonal faces which are in the front with respect to that plane. Okay. We are talking of a sub space now. It could be the entire 3D space or a small subspace in object space, and you have taken that small subspace which could be a spherical structure or a rectangular parallelepiped or anything you can visualize in this case, but of course, it will come as a rectangular parallelepiped here. We are doing something like an area subdivision in 3D. Okay, by splitting into two parts, and we have some planes on the front side, some planes on the back side with respect to a clipping surface either at the root node or any other node which are children, and then what you have on the left branch of the left subtree of that particular node, you have the polygons which are on the front, and the back side will have the I am sorry, this will be your left child, this will be your right child, and you will have the right child the faces which are on the back side or the outside the polygonal surface. So, that is what I repeat this sentence. In the tree, the objects are represented as terminal nodes with front objects as left branches and back objects as right branches. Continuing with the points of BSP tree, the BSP tree's root is a polygon selected from those to be displayed. This is what I was saying, that you do not need to imagine a polygon even to start with or any time later on when you are further subdividing with respect to planes. Take one of the existing polygons, and so the BSP's tree's root is itself a polygon, one of the n polygons. Okay. Okay. So, the BSP tree's root is a polygon selected from those to be displayed, and one polygon each from the root's polygon front and back half plane becomes its front and back children. This is what I was just saying, that you do not have to imagine a polygon. Select one out of the n, and the remaining n minus 1 is split into two parts, two categories. So, within these two categories, select one in the front and the one among those in the back, and that becomes the corresponding children of the root node, and this process continues recursively till you stop only at one where you have just one face to conquer, and there are no two faces, something like area subdivision, but in 3D. So, one polygon each from the root's polygon front and back half plane becomes its front and back children. The algorithm terminates when each node contains only a single polygon, that is true. Intersection and sorting at object space precision is the key idea. In area subdivision method, we worked in image space, this is completely object space. We do not worry about the image space at all, except looking at the viewing direction that decides the frontal and the back side sort of a thing. Of course, back face culling can precede BSP tree to help reduce the number of polygons which you have to process, all right. But after that, you just worry about the viewer direction. That viewer direction dictates what is going to be your brighter side to calculate the surface normal, and after that you just use one plane to split into two parts, split each of these planes further by the help of one polygon each from the selected from each of these categories, and so on, and you keep dividing till at the leaf node you are left with just leaf node cannot be a null pointer. Okay. In this BSP tree, it must be a single polygon, it should not be two polygons, it must be a single leaf node, must be one polygon, okay, from the list of n polygons. Okay. So, that is what you have. So, you can visualize that the average case for a BSP tree you can have log n complexity, whereas the worst case you can actually go to n even, we will see that. Intersection and sorting is at object space precision. Let us take an example. Let us take an example now, realist. As you can see here that there are basically 5 polygons numbered 1, 2, 3, 4 and 5. Remember, now we are looking not into some, we can look into this 3D scenario from an arbitrary direction, okay, polygonal planes, as if we are not looking always into viewer direction. No, that is not the case here, but I have purposefully shown the planar faces not like this in the case of as you have done for area subdivision method, but as if we are looking into polygonal faces in this fashion. Okay. And the view direction can be anywhere. We are just involved in taking a planar surface and splitting the object space or the entire 3D space into two parts. So, that is what we do with an arbitrary number 3. We select the plane number 3 and split the space into two parts, and if this is the frontal vector, the surface normal of the 3 pointing to the brighter side with respect to a viewer direction, then what you will have on the frontal part of the 3, you will have polygons 1 and 2, and you will also have to split the polygon 5, this was the polygon 5, into two parts, which will result in 5A on the frontal side and 5B on the back side. So, on the left, after the first subdivision with respect to polygon 3 as the root node, you will have 1, 2 and 5A as the children of the tree. Right now, it is not a binary tree in that sense, because there are 3 siblings right now, and so what will happen is on the back side of 3 you will have 4 and 5B. That is what will be the result of this. Okay. It is a tree with one root node as the polygon 3, and the left branch containing the polygons which are on the front side, which are 1, 2 and 5A. I am repeating, which I just said some time back, and the right pointer or the right subtree will have 4 and 5B. So, you need to split further because the nodes do not have single polygon. So, what do you do? Take the structure once again, look into the left hand side, which is 1, 2 and 5A, and use the polygon number 2 to split the space further. The frontal part of the subspace which is on the frontal side with respect to polygon number 3 as given here is split again into two parts with the help of the polygon number 2. So, with respect to the frontal side of 2, which becomes the left child of root node 3, you have 5A to your left and 1 as the right. That is correct. So, that is what you will have. Okay. So, that is what you will have with respect to the 3. If you use 2 as your left child for splitting the subspace into two parts, you will have 5A to your left and 1 on the back side. That is what you will have, and still the construction of the subtree is not yet complete, because the right child of the right subtree, in fact, of the root node 3 is not split, it has to be split further because it contains more than one polygon. If there was one polygon only 4 or 5B, that would have been the end of the BSP tree construction, but you need to select 1 out of 4 and 5B as your node for the root corresponding to that part of the subtree, which will be the right child for the root node 3. So, that is what we do. 3 has been selected to split first, then the 2, and then we select 4, and what will happen? The left is interesting to note, maybe I made a wrong comment earlier, the frontal part of 2 will be a null vector, will be a null pointer, because we do not have any node polygons to the frontal side of 4, back side you have 4B. So, that is what you have. So, 4, the node will not have any right, any left child, because there are no polygons to the frontal side of 4 with respect to this vector, normal vector. So, that you can have a null pointer with 4, and then you have the 5B to the back side. Okay. So, do not worry about this 5B vector normal here, that is not used in this calculation, but if necessary we could have used that as well. Okay. So, I hope this construction of this BSP tree is very clear to you, how you take one, split into two groups, then within the first group take another polygon, split into further branches, take the another partition, split into other branches, and so on, and you construct a binary tree. It becomes a binary space tree, or a BSP as it is called, because it is representing your 3-dimensional structure into 2 equal halves and subdivide and so on. That is what you are doing. Okay. Now, this is the question is now which will come to your mind is, what happens to this BSP tree if I had not started, if you did not start with the polygon 3 as your root node. If you have not started with polygon 3 as node, of course, you will have a different BSP structure. Remember, the scene does not change. Scene does not change, but you may result in a different type of a BSP structure completely. So, let us look at a particular example, but before that, this is the final thing which you will have, that when we are trying to consider now these 3 prospective polygons for splitting. Remember, the previous problem is over, where this was the BSP tree constructed out of these by choosing 3 first, then 2 and then 4. In that sequence you are choosing, and this is the BSP tree which you get. Now, I choose a different sequence. What is that sequence? I have labeled some of these with white color plate to indicate that is what I will choose. I will choose polygon 5, polygon labeled 5 as my first root node to split, and that you can immediately visualize what is going to happen, because if the front face of the 5 with respect to the viewer direction is pointing as shown in the figure, where there are no polygons to the front of 5, all the rest of the polygons will be towards its right subtree. The left subtree will be a null pointer for this particular BSP construction if you choose 5 and the front, either if you choose the frontal face as given or the reverse, one of the subtrees with respect to 5 would have to be a null pointer. It will not have any challenge. So, that is what happens with 5. So, we will continue this sequence and then construct the tree. We choose 5 first, then we choose 4 to further subsplit, then we choose 3 and then we choose 1. That is the sequence. Just remember the sequence. I will play it back for you. I choose number 5 first. Please note down the sequence. That is the one which is blinking right now. After the plane 5 or the polygon 5 has been chosen as your root node to construct the BSP to start with, I will then choose 4 to further split, then the 3 polygon, third polygon labeled or the polygon labeled 3 to further subdivide, and then the polygon 1 to further subdivide. If this is the sequence, I leave it as an exercise for you to visualize. You have already done the first step, where I chose polygon number 5, its left subtree will be null. I am sorry, with respect to the left subtree will be null, and the right subtree, okay, which is your right pointer, will have all the rest of the other polygons, and then we choose 4, 3 and so on. You will be having a structure like this. Very, very interesting. As you see here, remember the arrangements of the polygon in 3D space remaining the same, depending on the order which you choose, you will be reconstructing or constructing different type of BSP trees to represent the same structure. And this is easy for you to visualize, because as I said earlier, with respect to 5, its left subtree will be a null pointer. You will not have any children there, and then everything is towards its right because it is on the back plane. Similarly, with respect to 4, everything is on its back plane, nothing on the front. So, left pointer will be a null pointer for the left subtree for 4. With respect to 3, everything is in front, which is 1 and 2. So, the right pointer, the right subtree will be a null pointer for the node 3 here, and then with respect to 1, you have its again its left subtree, which is a null pointer, and the and finally finish with the 2, which is to the right child, the only leaf node available in this construction with respect to node 1. Remember, in the previous construction as given here, you had 5A1 and 5B. There were 3 polygons which were at the leaf nodes. In this case, there is 1 polygon which will be in the leaf node. So, it all depends on the order which you are choosing. That means, one point we must keep in mind here, which we will again discuss later on, maybe in the next class, that BSP tree is not a unique representation for a given 3-dimensional structure. Of course, if change the structure, the BSP tree changes, but for a given set of 3D polygons, if you do not alter the viewing direction and the positions and the orientations of a set of polygon, n set of polygons, whatever be the value of n, you can have different BSP trees or binary space trees constructed from these, okay, depending upon the choice or the order in which you choose the polygons. Depends upon the first one which you choose, get subgroups. Again, within the subgroups, if you choose different combinations, you can have many various possibilities of different BSP trees constructed. Which one is the best one? Why do you need a BSP tree to do a visible surface detection? That we should look first after the BSP construction, and then for this example we will come back and find out which one is the best one. So, what do? display list for a BSP tree. We need to display this list of polygonal surfaces in some order for a BSP tree to implement visible surface detection. And to do that, the BSP tree must be traversed in a what we call as a modified inorder tree walk. I hope you remember your data structure and algorithms concepts, where in one of the lectures you would have seen an inorder traversal. Okay? An inorder traversal is what you do, and then we will see what is a for this binary tree, and we will see what is a modified inorder tree. So, come back to this concept here, where we talk of a BSP tree may be traversed in a modified inorder tree traversal or walk to yield a correctly priority ordered polygon list for an arbitrary viewpoint to implement the VSD. What is this modified tree? If the viewer is in the root's polygon front half space, which is, that means you assume the viewer is to your left child, the algorithm for modified inorder traversal must first display all the polygons in the root's rear half space, that means towards his right child first, then the root, and finally all the polygons in the front half space. What was inorder traversal for a tree? Recursively defined in terms of left subtree first, then the root, and then the right subtree, isn't it? And this is recursively applied to the subtrees. I repeat again, inorder traversal talked of left subtree hierarchically, recursively, then the root node, and then the right subtree. Modified is just the reverse, where I first traverse just the reverse path, again recursively hierarchically, right subtree first, which is the rear half plane polygons first, because they are the back side with respect to the viewer. We are assuming here that the viewer is with respect to the root polygon which you have selected, with respect to that it is in the front half space. That is what you use to define the normal, the brighter side of that polygon surface normal, which you used to define. We talked about that when we selected the polygon and talked of this brighter side, darker side, select the surface normal, and based on that select the front partition and the back partition. So, you are or the viewer is in the front partition with respect to the root polygon in the BSP tree, and if that is done, display the ones which are behind is your VSD, Z ordering, depth ordering. So, display the one which is behind, then the root, and then which is in the front. So, you make the modified inorder traversal walk by doing your right child, then the root, and then your left child in your modified space walk. In the other case, in the original inorder, remember I repeat again, you would have had the left child first, then the root, and then the right subtree or child, whatever the case may be. In the modified inorder, the reverse happens. Okay, you start with the rear half plane, then the root, and then your left subtree. Okay, so repeat here again, visualize. We will do that. If the viewer is in the root polygons front half space, the algorithm must first display all polygons in the root's rear half space, then the root, and finally all polygons in the front half space. Of course, you must use backface culling prior to this to throw out all the back faces, then construct a BSP tree, then make a modified inorder tree walk, and then each of the root children is recursively processed in the modified inorder tree walk. So, this is the concept of the display list to construct a BSP tree and then walk through it, modified inorder traversal to have the correct ordering of this. BSP tree is not an order. Finally, you must have a sequential ordering. BSP tree gives a structural representation in a binary tree form of the space, and that is what is called a binary space partition tree or a BSP tree. You have to do a modified inorder traversal or a walk to have the correct ordering of the surfaces with respect to the viewer, and in this case we are assuming, remember, that the viewer is in the front partition with respect to the root polygon. That is what you do. Disadvantages: more polygon splitting may occur than in Painter's algorithm. Yes, because you are using polygon to split one another just like that without checking the area subdivision method. Of course, it may not be as bad as the area subdivision method, but with respect to Painter's algorithm you may have more splitting, and appropriate partitioning the hyperplane selection is quite complicated and difficult. This is the key idea. I just talked about a scenario where you may not have a unique representation of a BSP tree. That is fine. So, what is optimal? It is very difficult for you. We can spend a few minutes to discuss this, because based on the root polygon which you select to create the BSP tree, and then the further polygons in the different subgroups which you select, that is going to dictate what is your BSP tree which will come out. Whether it will have maximum depth or an optimal depth log n or even order n for n polygons will depend on two facts. Of course, the distribution of n polygons in space is number one. Number two is what is your choice. You can have a random choice, nobody stops you from doing that. BSP tree construction does not give you any guidelines to follow. You can randomly abruptly choose any polygon to construct the root, and then the further subtrees you please go ahead and do that, but you have to pay the price too. Two prices. First of all, you do not know the final outcome of the BSP tree which you are going to construct, and that could cost your polygonal spacewalk for the modified Inorder Traversal number one. And the computation burden in constructing the tree could be more costlier if polygons are not chosen in ordered form. How do you choose in ordered form? Then you have to compare each polygon with the rest of the n minus 1 polygons. That could even be more costlier if n is very large. If you need to compute whether you have an optimal polygon middle at position somewhere in the middle with respect to the other polygons, you have to find, if you have to find out computationally where is that polygon to construct an efficient BSP tree, that will be further costlier, because recursively you have to keep doing that for the two subgroups, further subgroups and so on. That is why BSP tree does not say do not try to find an optimal polygon, use a random one. Of course, there are some efficient algorithms to construct an efficient BSP tree outside the scope of these lectures in terms of research on BSP trees and partitions, but to choose that it could become a very big computational burden. You want to avoid that, because that could be costlier than doing this costlier modified Inorder Traversal work. You better construct a suboptimal tree or a very long depth tree which you have to walk more. That will be easier for you than trying to find out to construct an optimal BSP tree and at each stage finding out an optimal polygon to put it at the root of your subtree or the main tree. So, BSP tree does not give any guidelines, you can have a random one. So, depending upon your random choice, depending upon your scene construction, you are not going to have an optimal or a unique BSP tree. There does not exist any unique BSP tree for a 3D object representation in terms of n polygons, and not only that, the BSP tree which you construct is not only it is going to be random. It is not only going to be unique, it will have different structures based on your random choice, and that will give you different walks, but that walk could also result in different sequence of ordering, but it will give the correct depth in representation. I leave it as an exercise for you to check with those two examples which you have taken with 5 polygons, where we have 2 different ordering of different surfaces as root nodes, and we have constructed 2 different trees. Apply modified Inorder walk on both of these and see the order. See the order of the display list, are they same or not. Take this as a home assignment with those set of polygons, or even modify that structure of the polygons in 3D, come up with 2 different type of BSP trees construction based on random ordering, and then have a modified Inorder walk and see what is the result. Okay. So, that is where we conclude the discussion on BSP trees. With the small amount of time left, I will introduce the most important concept of VSD algorithms, which is called the ray tracing, and we will discuss most of this in the next class. Ray tracing is one of the most sophisticated methods, and if you see this particular figure, you will see that this concept is similar to the concept of Z buffer or depth buffer algorithm which we discussed earlier. Depth buffer also consisting of n polygons, but we worked in the object space. In the case of this ray tracing, we actually, it is a combination of object and image space, but mostly we work in image space. What is basically done is, this ray in depth buffer which we are talking about as a light ray coming out in a canonical view volume orthographic projection case, can be now visualized to be a ray coming out of a pixel from the projection plane xy and passing through all these polygons. Okay. And that is what we drew. We actually reverse trace the light path which is coming out of surfaces and projecting it onto our projection plane. We reverse the path of the ray of light and come out of the projection plane and enter into the object space, and that is what we look like. If you look at this particular diagram, which is I am using a funny creature for illustrating a visible surface detection ray tracing algorithm, we are talking about a image space on the left hand side. Grid of pixels here, and for each such pixel I have only drawn 2 rays, but if there are n cross n amount of pixels depending upon the resolution of the image buffer, there could be m horizontal rows and m columns or vice versa, you will have m multiplied by n different pixels in the image buffer, and you have to have reconstruct all the m multiplied by n different rays. So, in this case I am only considering in this figure 2 out of this m cross n different rays, and for each ray I drag out a ray in the reverse from the pixel array, from each individual pixel, trace the reverse path of the light direction. Remember, the light will fall on the object, we will talk of shading models, but you can imagine light rays will fall on this object and move towards the pixel array, but here I am reversing, I am going into a trajectory in a linear path in the reverse direction of the light. Okay. The light, remember, will fall on the object and hit the image plane, but from the image plane I am moving towards the object in the reverse direction of the light source, and find out, hit the object, hit the polygon and find out which polygon is hit first, and from that polygon find out the light source and shade it. Of course, we will not talk of any shading algorithms here, which we will be pushing when we talk of illumination shading, but right now the ray tracing involves taking a ray out of a pixel and going and hitting a polygon which will hit first. Let us say there is a polygon 1, polygon 2, polygon 3 and so on. So, you take a ray out and find out which polygon is hit first and shade that polygon. Do not shade the entire polygon, shade that particular pixel with respect to that polygon's illumination properties. So, that is what you do here. As you see, we will conclude this lecture with these 2 examples and talk of more points in the next lecture. When I talk of visible surface rendering, here a ray coming out of a pixel, orthogonal or projective perspective projection does not matter, and out of all these n 3 polygons here, we have to find out which is the first polygon which will be hit first, because that ray will not go and hit the other polygons, and that polygon will be used to render that particular pixel only. So, each pixel you will have a single ray, and that is what will be used to render that particular polygon. We will just wind up with a few points for Z buffer for each x and y z point on a polygon surface, which corresponds to the orthographic projection point x y in the view plane. At each point x y point on the projection plane, object depths are compared by using the depth buffer values, and for ray tracing, shoot ray from each point 2 pixel x y into the scene, intersect with all the surfaces, find the first one which the ray hits, and that is that surface which is used to render that particular pixel. We will start from this slide onwards in the next class and discuss details of the ray tracing, which is the most sophisticated among all the different VSD algorithms which we have discussed so far. Thank you very much.